Welcome everyone. Today, we'll explore the key factors that influence corrosion, a process that affects the durability and safety of metal structures. Understanding these factors is essential for engineers and industries to prevent costly failures. Definition and importance, economic and safety impact. Corrosion is more than just rust on metal, it's a critical issue with economic and safety implications. In this session, we'll discuss what corrosion is, why it matters, and how it impacts industries worldwide. Corrosion is the gradual destruction or deterioration of materials, usually metals, through chemical or electrochemical reactions with their environment. It is a natural process that converts refined metals into more stable forms such as oxides, hydroxides, or sulfides. Understanding corrosion is critical because it affects the durability, safety, and functionality of structures and equipment. Corrosion can lead to catastrophic failures in bridges, pipelines, and industrial plants, resulting in economic losses and safety hazards. Industries spend billions annually on corrosion prevention and maintenance, highlighting its significance in engineering and material science. Corrosion has a profound economic impact, costing industries and governments billions of dollars each year in repairs, replacements, and preventive measures. Beyond financial implications, corrosion poses severe safety risks. Structural failures caused by corrosion can lead to accidents, environmental contamination, and loss of life. For example, corrosion in oil pipelines can result in leaks, causing environmental damage and operational downtime. Understanding these impacts emphasizes the need for effective corrosion management strategies to ensure reliability and safety in critical infrastructure. Electrochemical process. Corrosion primarily occurs through electrochemical reactions. Let's look at how this process works and why it's important for engineers to understand. Corrosion primarily occurs through electrochemical reactions where metal atoms lose electrons and form ions. This process involves anodic and cathodic reactions. At the anode, metal atoms oxidize, releasing electrons, while at the cathode, a reduction reaction occurs, often involving oxygen or hydrogen ions. The presence of an electrolyte, such as water containing dissolved salts, facilitates electron flow between these sites. Understanding this mechanism is essential for predicting corrosion behavior and designing effective prevention strategies. Several factors influence corrosion: material properties, environmental conditions, electrochemical factors, and mechanical stress. We'll examine each in detail. The composition and microstructure of a material significantly influence its corrosion resistance. Pure metals often corrode faster than alloys designed for corrosion resistance. Factors such as grain size, phase distribution, and impurities can create localized electrochemical cells, accelerating corrosion. For example, stainless steel contains chromium, which forms a passive oxide layer that protects against corrosion. Understanding material properties helps engineers select appropriate materials for specific environments. Environmental factors such as humidity, temperature, and the presence of pollutants play a crucial role in corrosion. High humidity and temperature accelerate chemical reactions, while pollutants like chlorides and sulfur compounds increase the aggressiveness of the environment. Marine environments, for instance, are highly corrosive due to salt and moisture. Engineers must consider these conditions when designing structures and selecting protective measures. Electrochemical factors such as pH, oxygen concentration, and conductivity of the electrolyte influence corrosion rates. Acidic environments generally accelerate corrosion, while oxygen availability affects cathodic reactions. High conductivity in electrolytes, often due to dissolved salts, facilitates electron flow, increasing corrosion speed. Monitoring and controlling these factors is essential for minimizing corrosion in industrial systems. Mechanical stresses, including tensile and compressive forces, can exacerbate corrosion through mechanisms like stress corrosion cracking. Poor design features such as sharp corners, crevices, and dissimilar metal contacts create localized corrosion sites. Engineers must incorporate stress analysis and design optimization to reduce these risks and enhance structural integrity. One special type is galvanic corrosion, which occurs when two dissimilar metals are in contact in an electrolyte. Let's see how this works. Galvanic corrosion occurs when two dissimilar metals are electrically connected in the presence of an electrolyte. The more active metal becomes the anode and corrodes faster, while the noble metal acts as the cathode. Common examples include steel and aluminum in marine environments. Preventive measures include using insulating materials or selecting metals with similar electrochemical potentials. Prevention is better than cure. Protective coatings and smart design are key strategies to combat corrosion. Preventing corrosion involves applying protective coatings such as paints, galvanization, or polymer layers to isolate the metal from the environment. Design strategies include avoiding crevices, ensuring proper drainage, and minimizing contact between dissimilar metals. Regular maintenance and monitoring further enhance corrosion resistance and extend the lifespan of structures. Let's summarize the key takeaways from today's discussion. Corrosion is a complex phenomenon influenced by material properties, environmental conditions, electrochemical factors, and mechanical stresses. Understanding these factors is essential for designing durable structures and implementing effective prevention strategies. By combining material selection, protective coatings, and proper design, industries can significantly reduce corrosion-related risks and costs.